Hi, welcome back. In this lecture, I want to give you an overview of the technologies and the methods that we're going to work on this third module that is about quantum neural network. So the discussion that I'm going to do today is really how we can move from a classical description of neural network to the quantum neural network. So I'm going to provide a high-level overview how classical neural networks and generalize to quantum neural networks or QNNs in short. We will see that the pipeline, the different steps during the neural network training and inference are basically the same. We're going from data preparation to data processing, data output, and then we loop around. The major difference between QNNs and classical NNs is that the QNNs replace the classical layers with the quantum circuit. However, the classical optimizer is still in the loop, so we're going to use classical optimizer in combination with the quantum circuit. Later on in the following lectures, I will go deeper in the different aspects of this lecture. However, I want to give you now as the big overview, the big picture of the quantum neural network. As I said, the classical neural networks and the quantum neural networks, they share the very same pipeline, the different stage. We go from data preparation that includes normalize, scale features, encode categories, and create training batches to data processing. This consists of a feed-forward step through layers with weights and nonlinear activation, and then we have the data output that compute the prediction, for instance, probabilities and class label. These different steps are embedded into a training what it does is to compare prediction with targets using a loss function and update weights via an optimizer. So this is the classical step. The very same works in the quantum version of it. In this table, I compare the two approaches. On the left part, I have the classical neural networks, and the right column I have the quantum neural networks. Quantum neural networks we saw in the quantum SVM. They encode data using quantum circuits, so-called feature maps. So the classical data is encoded into the quantum state via feature maps. The model of the neural network consists of two parts. One is the feature maps that encodes the classical data into the quantum state, and then we have a so-called variational circuit V of theta that allow us to calculate the prediction by changing this tunable parameter that we call the theta. In the case of quantum neural networks, the parameters are the gate angles and the rotation parameters aids. Instead of having weights and biases, what we're going to do is to adapt and tune theta, so we minimize the loss function. The forward pass, which in a classical neural network consists of matrix multiplication and activation, corresponds to quantum state evolution after application of the encoding quantum circuit and the variational form quantum circuit. Finally, we are going to have the output. In the case of quantum neural network, we have measurement outcomes and expectation values. So we get one scalar out, so we can calculate the loss function. And the training loop is nothing else than a hybrid loop where we have execution of quantum circuits and an optimizer that is classical. The very first step for any neural network, including quantum neural network, is the data preparation. We saw in the quantum support vector machine that the way to go from the classical state, the classical data, including all the features, into the quantum states is by using so-called the feature map circuit. The feature map circuit, we initialize the quantum circuit with a zero state, and then we feed in the classical input as angles of our gates. The result of the quantum circuit is a quantum state that we see here in the cat form using 5. So these are not trainable parameters that we're giving to this circuit. These in particular are the initial data that we want to encode in the quantum state, and we encode it by using angles. The new part with respect to the quantum support vector machine that we saw in the previous model is to include an additional quantum circuits. So we have a feature map, and then we include another part of the quantum circuits that has different parameters that are tunable. What it means tunable? It means that the parameters can change during the training process. So at each training step, we have a forward pass. We calculate We do a measurement, we calculated the logs, and we use the loss function to calculate the new values of these parameters. So these are new values. It means that these values are tunable. It means that we can change, and these values are the parameters of our quantum circuit. So all these theta here, you see here, theta naught, O1, so on and so forth. All these are so-called Q and N parameters, and these are the equivalent to the weights and biases in the classical neural network. So we will spend the next lecture going in deeper in this second part of the quantum neural network, the variational circuit. After we have done the variational circuit, so we go from feature maps, we get the quantum state, then the variational form quantum circuit is taking the output of the feature maps and is giving output another state. So what we need, another quantum state, so what we need is a measurement in order to provide some values to the loss function. So we provide a measurement. Typically this is observable that we are going to call M, and it can be local or global depending on how many qubits we are going to calculate. So for the binary classification, we often measure a single qubit and interpret this output as a score or probability after we did the scaling. So this is very similar to the neural network. The major difference is that we use two circuits, one feature maps, variational form. At this point, in order to get an output, we do a measurement. So what are the difference between feature maps and variational form? So these are the one that we saw in the quantum support vector machine. So the major difference is that the parameters that we give to the quantum circuits are not tunable in the case of feature maps. It means that during the training they do not change, but also these parameters are actually the classical input data, right? So are the different feature that we want to encode into quantum state. The parameters have a very different role in the variational form. So these are parameters that we are going to change as part of our training process. So this is the major difference between feature map and variational form, is that in the variational form quantum circuit, the parameter theta that we give to our quantum rotation gates are actually trainable. So we can update during the training in response to the learning. The variational form are also called ansatz. So you will find a lot this term in literature, and there are nothing else than parameterized quantum circuit. So the structure is actually given. What we are going to do is to calculate this parameter of our quantum circuit. So to summarize and finish up this lecture for today, the quantum neural network resembles the classical neural network. What we do, we start with feature maps that encode the classical data in this feature vector that we call X, and then we create a quantum state that we call phi in the cat notation, and this quantum state feeds into another variational form. The input to this variational form are a stack of theta values, and these are corresponding to the weights and bias. These are the values that we can change in response of the learning. We do the measurement, and here we calculate a loss function. Then we use this loss function to calculate new values of the theta. This is the last slides of this lecture, and talk to you soon.